let me talk about a favorite. An IMAX theater screen. That's a nice vertical surface. I like that. Beautiful art. I grew up in Chicago. This hangs at the Art Institute. I sat in front of this Seurat many days. Actually, just peering into the small dots and very small sections really got me interested in patterns and pattern making and mathematics and all sorts of very fun ideas, but very beautiful art. Favorite surface? It's three-dimensional, but up here right now it's just a two-dimensional surface. For those of you who don't know, that's the TARDIS from Doctor Who. I've been watching Doctor Who since the second Doctor. I'm not an imposter. All right. I'm enough. Okay. Another favorite surface that just actually came up is the mid-boss surface at the moment of tearing. Quite a very good surface. Thank you so much. You're welcome. Okay. Some of my not-so-favorite surfaces. So, believe it or not, this is one of the classrooms that I teach in. And just so you know that on one of the walls there are whiteboards and a smart projector. But the rest of it, as you can tell, is windows and surfaces that I'm not allowed to tape anything on. Here's another classroom that I teach in. I just went yesterday because, you know, I decided the day before yesterday I'm going to give a talk, so I had to go take some pictures. And so it doesn't normally look like this, but this is a classroom at my school, and it has very little vertical space in order to get the kids up and working. Now, just so you know that that's not how all the classrooms look, there are classrooms that look like this, that have beautiful vertical surfaces. Unfortunately, I don't get to teach in those rooms. I think it has something to do with me being the only one on Twitter that will. Or it probably has to do with seniority. All right, so the problem is, I really think about mathematics and science, or for that matter, anything that you want to learn, isn't really about specifically the numbers or the equations, the computations, algorithms. It's really about understanding and being able to explain your understanding in a way that others know that you understand something. So the only way to do that is to get people up on surfaces to be able to visibly show what they know. So finally, here it is, my favorite math surface. Oh wait, it's too big, let me zoom in. There you go. It's a whiteboard, right? So just a simple, the best interactive surface, sorry, Smart Technologies. It's a 2 by almost 2 3/4 foot smartboard. I use centimeters, but that's because, I don't know, I like centimeters. Yeah, all right, I get them from Lowe's or Home Depot. They're basically just panel board. They're bathroom panel board, bead board. It's $13.50 a sheet. You have them cut it, tell them you're a teacher, they'll do it for free. You get 6 whiteboards. So it's about $2.50 and, you know, 2 and change, so I just rounded up to $2.50. And they're non-permanent vertical surfaces. You can put them anywhere. You can put them on blocks on the desk, which is what we do, because you can imagine you can't hang them anywhere. But if you could drill holes in them and hang them on hooks. You could put Velcro on the back and Velcro to put them up. You can lean them against the wall, against a chair, against your legs. You can take them outside. You can take them to the library. You can take them wherever you want to go. So you can have random grouping and random non-permanent vertical surfaces all the time. This is my favorite, my very most favorite vertical surface. So let me show you a few examples. Right up. First, so why is that important to me? Because I like to model stories. We tell stories, and I think that's really what we do, is we tell stories all the time about our understanding. And I want to make math real, so about a physical phenomenon, and you put these models that you create on whiteboards so that their understanding is visible, so they can defend it, argue it, explain it, use multiple representations, start off with a big, messy problem, ask questions, make assumptions, divide problems, identify things they want to test, what mathematical tools do they use, And can they explain it and extend it and test it, which is fantastic, which is what I like to do a lot. So here we go. Let's look at a few examples. I guess at this point I should probably tell you that I'm not a math teacher by training. This is a second career for me. I was a research scientist and professor of biochemistry, biophysics, and applied mathematics at UCLA Medical School, and then the Ohio State University Medical School. Administrator said, duh. Those of you who are from Ohio know why I had to do that. So I like to use science and math together. So students, so in this case, this is a pre-calculus class analyzing circuits that we actually did in our class. So they collaborate to do experiments, collect data, and sometimes it's not in my class, it comes from their science class. So now we're collaborating between math and science on a regular basis. Each group represents their understanding, diagrams, graphs, algebraic expressions, verbal explanations. They argue and debate their understanding until they have a common understanding of what they think is going on. It's actually really great. I know it's really, really difficult to see, but there's systems of linear equations on there. Right? It's kind of fun. This is called Kirchhoff's loop rules for anybody who's really interested in the physics of it. Can't see this at all, but this is algebra 2. It's weight versus mass relationship. Is there a relationship between weight and mass? You can see there's a linear relationship there. It's actually pretty nice. Questions like, what does the slope represent? Turns out it's it's G, which is the gravitational force of acceleration due to gravity. So on Earth, it's 9.8 meters per second squared. What does the vertical intercept or y-intercept represent? If anything? Should the graph go through the origin? Will you get the same result on the moon? These are some of the questions that we pose to each other, and we try to figure it out, kind of argue and debate. And there's a lot of information on there. Each kid had a different color in this one, and there you can tell their contribution to the board. It's pretty cool. Here's a trig pre-calc. So I have, believe it or not, flying pigs. Pigs can fly. They're little pigs. They hang from the ceiling, and their wings flap, and you give them a push, and they actually rotate. It's actually pretty fun. So flying pigs hanging from the ceiling with only a stopwatch and a meter stick determine the velocity of the flying pig 2 different ways, with vectors and with trig. And then are they the same? Are those velocities the same? Why? Explain. Right? So they have a little pig, and you can see there's 2 different representations. I only have one of the 2 boards. The explanation was on the second board, which I didn't put on here because I wanted this to be larger. I'm losing my. Okay. Here's calc. So I proposed you dropped a roll of toilet paper, and as it drops, it started to unroll. You think this could be a great calc problem. So Iron Chef, we iron stuff all the time. For those of you who don't know what Iron Chef is, there's a secret ingredient, and they have to make 5 different dishes using the secret ingredient. So when we Iron Chef something, they have to do as many different ways of showing their understanding of the problem of whatever the situation is. So here, I asked them, I wanted them to do as many different ways they could. So they use torque and forces, they use non-integration, so that would be the parallel axis theorem, and then integration, which is on the 3rd panel, and then their explanations on the 4th panel, to get their understanding out, which is pretty good. And they determined that the acceleration as it unrolls is not 9.8, which is the acceleration due to the gravitational field, but 6.1. What happened? What's going on? I have to explain what they think is what's happening. So you can imagine they have to actually do a lot of work. It's not just the math, it's the physics and the understanding that they also have to think about and integrate from their math class, from their science class, or go figure it out and figure it out together. It's actually fun. I like these kinds of things. Here's motion with acceleration. Battery-operated car moves with constant speed. They've already shown that it has constant motion, has a constant slope. Well, what about a cart that's coming down a ramp from rest? Will it have constant motion? You hypothesize that there's no difference. Design an experiment to test that. Right? Turns out it's parabolic. When in Algebra 1 did they see a parabolic slope? Right? It's actually pretty cool. It's fun. One that I really like to do is games. So this one is actually kind of fun. I usually try to do this with one of my classes at the start of the year. which is, I got a new game, I have a game that I got last year, but last year's class took out the rule book, and they replaced it with a sheet of paper with 4 games where they put all the moves down. Your challenge, they're challenging you to figure out the rules. So now it's about play the moves, try to figure out, well, what are the rules of this game? What are you pretty sure of? What are you kind of sure of? What are you not sure of? Are there more than one way to actually develop rules to play this game? How confident are you in or how sure of you? We talked about that here, of your rules that you've defined. Can you then have somebody else play the game? It's actually kind of fun. Notice where this whiteboard is, it's on a couch, right? So, yeah, like that. I'm going to skip that one and say, so basically, whiteboard discussions are really Socratic dialogue. That's what I'm talking about. All right, so students explain and defend their models of understanding. Do all the representations that they're using tell a consistent story? That's where we need to get to. Do all of your representations tell a consistent story? And they learn the strengths and weaknesses of different representations. Not every representation is going to tell a whole story. But maybe it's a much richer story if you actually have multiple representations together, as opposed to just one. Right? And if you can tell a story from multiple perspectives, then you really understand what's going on, which I really like. So they compare, argue, debate their models with their peers until they have a consensus. And if you want more info of my most fave, which are whiteboards, I made a Tina URL that has a folder that has how do you get the whiteboards, how do you make the stands, prompts for Socratic dialogue, different ways to use whiteboards in your discussions and debates, like the mistake game is one of my favorites. How to care for your whiteboards, believe it or not, care for them, but they were great. So, and I'll end with a Dr. Who quote here. We're all stories in the end. Let's make it a good one. And I would just say together. Let's make it a good